In this video, we present our approach to capturing an object's spatially varying reflectance properties using a linear light source reflectometry apparatus. In our technique, we pass a linear light source over the object, such as this test sample with spatially varying diffuse, specular, and specular roughness parameters. During this time, a digital camera records an oblique view of the object as the light moves across it. For each pixel, we can graph its RGB pixel values as the light passes over the object, shown below. In this visualization, dragging the mouse along the graph plays through a movie of the light moving over the object. Since we know the geometry of the camera, the light source, and the object, we can predict the position of both the specular and diffuse peaks in each pixel's reflectance trace, shown as magenta and cyan vertical lines. We determine the pixel's diffuse color by measuring the height of the graph at the diffuse peak. We use this to subtract a Lambertian model of the diffuse peak from the graph, leaving only the specular peak. We measure this peak's height and width to compute the pixel's specular intensity and roughness. Our process produces three independent reflectance property maps for the object, including its diffuse albedo, specular intensity, and specular roughness. Using hardware pixel shaders, we can visualize this virtual version of the object in real time under point light source illumination. The visualization shows the spatially varying diffuse color, specular intensity, and specular roughness for the different surfaces, including a thumbprint in the center of the object. For comparison, we rotated the original test sample in front of a camera under point light source illumination, finding the visual appearance consistent with rotating the virtual object under the same lighting conditions. For our second example, we extended our technique to capture the appearance of an illuminated manuscript. This circa 1460 page from the Book of Hours features different colors of ink as well as embossed gold lettering. Since the page does not lie flat, we added a simple 3D scanning system to project a red line just behind the diffuse peak. After the pass of the light source, we turn on a fluorescent backlight, which allows us to record the translucency of the manuscript's vellum material. In our data analysis, we determine the height of each pixel of the manuscript by detecting the left-right position of the red laser peak in the reflectance graph, as seen at the right. For the specular component, we detect the height, color, and width of the specular lobe, as well as its left-right shift with respect to the mirror angle to determine one component of the surface normal. By scanning the manuscript at two diagonal directions, we can estimate complete surface normals at each pixel. With this extended process, we can recover 6 channels of per-pixel reflectance information, including the diffuse albedo, specular intensity, specular roughness, displacement, surface normal, and translucency. Here we use our real-time rendering program to display the additional reflectance channels, as well as to render the object in its three-dimensional form using the recorded displacement map. In particular, the rendered manuscript shows the recovered properties of the embossed gold lettering, glinting when the light source appears at the appropriate angle with respect to the camera. When the light source moves behind the object, we see the manuscript's translucent properties. Looking closely and moving the light source, we can see the embossed effect of the captured surface normal variations. Again, we photographed the original manuscript rotating under point light source illumination to serve as a comparison to the virtual version, including the page's translucency at the end of the sequence. The virtual version shows the same reflectance properties under rendered point light source illumination, even though the reflectometry apparatus observed only a one-dimensional pass of the linear light source. As a result, the linear light source capture process can be simpler, faster, and more robust than traditional reflectometry approaches.